In this video, we present a new approach called SA6D to solve 6D pose estimation on novel objects without a training, and provide a robust estimation in cluttered scene, even though the object is heavily occluded. Novel object pose estimation can be interpreted as a future learning problem. Namely, every time the estimator predicts a pose of a novel object in arbitrary scenes by only giving a few reference images with the ground truth pose of the novel object.
Generalizable 6D pose estimation on novel objects without the need of retraining is important for robotic grasping.
However, current approaches do not work well on occluded objects. Furthermore, they require object-centric reference images or prior object information such as object center or segmentation, which limits the generalization. In this work, we significantly improve the performance against occlusions without requiring cropped reference images or any form of prior object information. Furthermore, we achieve state-of-the-art performance using fewer reference images. SA6D comprises three submodules, namely an online self-adaptation segmentation module, a region proposal module, and a refinement module. In the segmentation module, there is a base segmenter and an updated segmenter. The updated segmenter is initialized by copying the base segmenter. Base segmenter first predicts the segments of each reference image. Afterward, an object model is reconstructed from the depth image based on the selected segment of the novel object given the ground truth pose of the novel object. Subsequently, the cropped region of interest of each reference image with respect to the novel object is computed. Meanwhile, the updated segmenter updates iteratively based on the reference images and identifies the segment of the target novel object. Based on the predicted segment, and local object reconstruction from the test image is computed. Afterward, the ROI of test image is computed using a global registration, which helps remove the ambiguity of the visual similarity against occlusion and other distractors in Gen 6D. The cropped reference and test images will then fed into the pre-trained Gen 6D detector to predict an initial pose. Thanks to the induced global and local object model, the pose is further refined using ICP. Therefore, how to enable a model to learn to recognize the target segment in an online fashion is crucial. Specifically, given the ground truth pose of the novel object, the segments from reference images are separated into positive and negative sides, where only the segments including the novel object are considered as positive. The updated segmenter is used to identify the target segment. For each reference image, it predicts a dense feature, which is grouped by the segmentation from base segmenter. The dense features are then grouped and averaged by the segmentation in order to get an object-level representation. Afterward, a contrastive loss is employed on the object representations to update the segmenter 5-star. This updating process lasts for n iterations. A target object representation is then averaged over all positive object-level representations. Given a test image, the object-level representations are computed in the same way. By comparing the similarity between the target object representations from reference images and each candidate of test image, the segment with the highest similarity is selected and used to reconstruct the local object point cloud.
We conduct evaluations on various tabletop object datasets, which have never shown during training, and compare against category agnostic and category level baselines. SA6D outperforms all baselines, especially against occlusion, although it is not trained specifically on each category like category level baselines.
We show examples that our proposed online self-adaptation module can segment target object with severe occlusions and with explainable confidence score by computing the similarity. Note that in the first example, since the object center of cat is occluded by driller, the ground truth segmentation selected on the wrong object, while the predictions can still find and identify the right segment of cat with the highest score.
We show the qualitative comparison against category agnostic baselines. The green bounding box denotes ground truth pose. Blue one is the prediction in baselines and the prediction of SA6D before using the geometric features in the refinement module. Red one denotes the final prediction of SA6D combining geometric features. Baselines struggle with localizing the target object compared to our method on occluded scenes. We also show the comparison against the category-level SOTA method, RepoNet, on Wild6D dataset. Note that RepoNet is trained and tested specifically on each category.
We show the accuracy with different number of reference images as input. Notably, SA6D gives meaningful predictions with one shot, while baselines cannot. Furthermore, we show the performance with different number of online iterations in the self-adaptive segmentation module. The visualized cropped region against Gen 6D indicates the importance of geometric features for occluded scenes, where the red cross denotes the target object. Please look at our paper and supplementary material for more results. Thank you.